Assalamualaikum. Hi everyone. Okay, in this video, we are going to do one beam example analysis of indeterminate beam using flexibility method. In this example, I will focus on one redundant beam. Okay, let's look at the example together. Okay, in the diagram, as we can see, it is a continuous beam. Okay, there are two roller support and one pin support. Okay, so we have to analyze this beam to calculate the reaction at all support, at support A, support B, and support C. So since this beam is a continuous beam, there are four unknown reaction which we calculate from which we calculate from support one here, another one here, and two here. So total are four unknown reaction. Four unknown reaction. So these four unknown reaction we cannot analyze using three equilibrium equation. Okay, so the first step we have to identify degree of indeterminacy, and the formula to identify degree of indeterminacy is quite straightforward. It is just the difference between number of unknown reaction and the three reaction that can be solved using equilibrium equation, three equilibrium equation. So I have explained here, I have written here, 4 represent number of unknown reaction, 3 is number of reaction that can be solved using three equilibrium equation. Means that 3 can be solved using three equation. Now it is 4. So 4 we cannot solve using three equilibrium equation. That is why we have to apply another equation, and that equation actually we derive based on the principle of superposition. Okay, and from that we derive what we call as compatibility equation. Okay, and the derivation of compatibility equation I have explained previously. Okay, so the difference is 1, so means that there is one redundant in this beam, and we have to identify, or we have to choose redundant. We have to choose one from 4 unknown reaction as the redundant. Let's say in this example, I have chosen By as redundant. Okay, so the compatibility equation, as I explained previously in my previous video in previous class. Okay, the compatibility equation is actually based on displacement at redundant position. Displacement at redundant position. Okay, now the compatibility equation is delta 1 naught plus F11 times By equal to 0. Delta 1 naught is the standard form of displacement in primary beam. F11 is the standard symbol, the standard form of displacement in redundant beam, and By is the redundant chosen. So this is equal to 0. This is actually displacement in redundant position based on the principle of superposition, as I explained earlier in previous class, in previous video. Okay, so next, inside this compatibility equation are displacement, and there are delta 1 naught and F11. Both are displacement. Delta 1 naught is displacement in primary system, primary beam. F11 is displacement in redundant beam. So how we identify this? Delta 1 naught, okay, the naught symbol represent primary system, primary structure. Okay, F11 belong to redundant structure. We identify from the symbol F that we use. F is actually displacement in redundant system. Okay, so there are two displacement, delta 11 and F11. So one belong to primary beam, primary system, and another one is redundant system. And we adapt and also adopt, okay, what we actually do in the topic of principle of virtual work or unit load method. Okay, so this displacement can be calculated by integrating moment equation from two structures. Okay, so the first structures is called as primary structure, and the second one is called as redundant structure. So we have two systems. One is primary structure, another one is redundant structure. And always remember, symbol node that we use is always represent the primary structure, and another one will be the redundant structure. Okay, so for the formula, actually we don't have to remember, because by looking at the notation that we use, delta 1 node means there are two label here, 1 and node. 1 and node means M1, M node. So M1, M node, we have to integrate M1 and M node. And for F11, we use 1 and 1 here. So it represents M1 and M1, M1 square. M1 square. Okay, so M1, M naught is symbol for primary structure. So M1 is primary structure, M naught is primary structure, M naught is primary structure, and M1 is redundant structure. So label 1 we get from R1. Okay, that is why we use M1. Okay, so these are the formula we integrate to calculate displacement. So we start we have to, so after this is moment equation. So for moment equation, we will get from two determinate structure, because after we remove redundant, the beam becoming the determinate beam. Okay, either simply supported beam or cantilever beam will be depending on the redundant that we have chosen. And in this case, we remove by, the beam is a simply supported beam, just like this. Okay, means that we remove by from the system. So this is primary beam. So what is inside primary beam? Okay, just understand like this. After removing redundant, it is become determinate, it is stable. So what is remain? All external loading remain. All external loading remain. So in this case, there is only one external loading, 10 kN per meter UDL remain. The only thing that we remove from primary beam is only by, the redundant. So now it is simply supported beam. We have one roller, we have one pin. So from this we can calculate reaction at both A and B, both support. And from reaction we can write the moment equation. Okay, remember the procedure start from reaction, and after that is internal forces. So moment equation is part of it, and we calculate displacement from moment equation. So we analyze primary beam, we calculate reaction in order to determine or to write the moment equation. Okay, next one is redundant beam. It is also called as redundant by applied. You can also write redundant by applied. It is representing redundant beam. Okay, what is inside redundant beam? Okay, we have to remain same type of beam. If in primary beam, it is simply supported beam, redundant beam must be simply supported beam as well. But what is different here is there is no external loading. There is no external loading. Okay, we will apply a unit value of by. We will apply a unit value of by. There is no external loading. We have analyzed it in primary beam. So in redundant beam, we only have the same system, but it is only subjected to a unit value, redundant beam. Okay, looking at this diagram, it is just like a virtual system. A determinate system subjected to virtual load. But this time, it is determinate system subjected to a unit value of by. A unit value of by. Okay, so from this, we calculate reaction due to a unit value of by. We can calculate reaction at A, reaction at B, and from that, we will write the moment equation in redundant beam, and it is called as M1. It is M1 because by is R1. So, it is M1. Okay, so all the moment equation. So, we have moment equation M0 from primary beam. We have a moment equation M1 in redundant beam. So, we summarize the moment equation in table form. Okay, since we have two cutting section, we have member AB and BC. We have AB and BC. Okay, we choose origin. Okay, we set limit based on origin, and we write the moment equation M0 and M1. Okay, so this the moment equation. So from this this is the moment equation that will be used in the formula, in the displacement formula. Remember, delta 1 node is M1 M0. M1 M0. So we have two cutting sections. So we have like this, and the value is negative 168.75 over EI. Remain EI as constant, and F11 is M1 square. So M1 square, we have two cutting section AB and BC. So the F11 is equal to 4.5 over EI. Okay, so these two displacement, we need to substitute into the compatibility equation. Okay, remember, first step we choose redundant, right? And after that, we write the compatibility equation, the standard form. Okay, so delta 1 node and F1 plus F11 dot by is equal to 0. So now we already have delta 1 node and F11. We substitute this value, so we get the compatibility equation. Okay, so what is the next step? Remember, the goal, the aim is to solve the problem. And the problem is the redundant. Because we cannot determine 3 unknown reaction because of this redundant. So we need to determine redundant first. So redundant we determine by solving compatibility equation. So we rearrange back. So we get by is equal to 37.5 kilonewton. 37.5 kilonewton. Okay. So after getting this by value, is this the end of analysis? The answer is no. Remember, we have to we have to determine all reaction. Remember, we have this beam, okay, like this. Okay, now we get By equivalent to 37.5. So we have Ay and Cy. This one is 0 to be determined. Okay, and after getting the 37.5 at point B, the redundant, we can continue to solve Ay and Cy using equilibrium equation as usual. Okay, so after we determine Ay and Cy, then only the end of analysis. And actually we can continue a little bit to draw the shear force diagram and bending moment diagram. Okay, so this is flexibility method. Remember, flexibility method we use whenever we have one indeterminate structure, whenever 3 equilibrium equation is not enough to calculate the reaction, then we have to apply flexibility method. In flexibility method, we have to identify redundant. Because redundant is the problem, so we have to determine the redundant first. And the redundant we determine by solving compatibility equation, which we actually derive from principle of superposition. We name it as compatibility equation. By solving compatibility equation, we can solve remaining reaction using equilibrium equation, and we can also solve remaining reaction using principle of superposition. Okay, how to calculate remaining reaction using principle of superposition? Do you want to know? Okay, so since I believe everyone knows how to solve this using how to solve Ay and Cy using equilibrium equation, I would like to focus on how we can solve Ay and Cy using another alternative, which is called as uh, principle of superposition, which is actually quite straightforward and easier than using equilibrium equation. Okay, so let's doing that. Okay, so remember the primary beam and redundant beam we actually get from principle of superposition. Okay, in principle of superposition, it is actually come from actual beam is equal to primary beam plus redundant beam. Okay, this is based on the principle of superposition. So the primary beam is UDL, okay, where we have primary beam is simply supported beam subjected to UDL 10 kilonewton per meter. So this is 6 meter long. So reaction here is 30 kilonewton and 30 kilonewton for the primary beam. For redundant beam, it is same type of beam subjected to a unit value of redundant, a unit value of By, a unit value of By, a unit value of By. So from that we determine 0.5, 0.5. Okay, so from the principle of superposition, we actually plus these two. And remember, okay, 30 is a 30 here. Okay, this 30 is AY in primary beam, and 0.5 negative 0.5 is AY in redundant beam. Okay, so we just need to plus to use the principle of superposition. It is just like this. Okay, this 30 plus 0 negative. It is negative 0.5. We have to time with BY 37.5. Then we will get AY. AY. So for AY, for BY, we just need to use we just need to use principle of superposition. For AY, we have to look at AY in both primary and redundant beam. So we plus these two, but don't forget for redundant beam, we have to times with BY value. We have to time with BY value. So same thing goes to CY. So another one is CY. So in this example, the value are the same. Okay. So that's all for this example. So we will continue in the next video for more example. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.